Welcome back, everybody, to section 3. This week we're just going to be covering folds. So, first things first, what type of stress? Remember, we talked about extensional or tensional stress, we talked about compressive stress, we talked about shear stress. Which type of stress do you think cause rock layers to fold? Example for this one. So if we take something like this, a rock layer, and we pull it apart, is that going to cause it to fold up? No. What if we take this and we shear it, so we press on the surface of it like this? Is that going to cause it to fold up? Not exactly. What if we take it and we compress it from the sides like this? Now what we get is something that is folded. So in rocks, this is what it's going to look like here. So just like a sheet of paper here, we have rock layers which have been folded and bent up into these curved shapes. It's a bend or a warp in some sort of layered rock. For the most part, these are caused by compressional stress. We're pushing inward on the rocks somehow. By and large, when we're talking about folds, we are talking about sedimentary layers. Not exclusively, but that's the usual case. Faults, you should think of sedimentary layers unless given more information otherwise. Usually, when we find folds, we don't just find one isolated fold in the middle of nowhere. We're going to find many, many different folds of different types that are complementary somehow. And in a little bit, I'll show you exactly what that means. So, fold deformation. This is ductile deformation. We haven't broken the rock, we haven't snapped it, we're not breaking it or fracturing it in this sense. Instead, slowly bending it or molding it into these sorts of shapes. This is more common whenever the rock is hotter, so deep below the surface, where we have a lot of pressure, and whenever we have very, very slow rate of deformation. So we're not putting a whole bunch of force on it all at once. Instead, the force comes on slowly, and bends it into these sorts of shapes, like with folds. Composition. Folds can happen in any sort of rock. Usually, though, we're talking about sedimentary layers. So what is this that we're looking at here? This would be an example of an anticline fold. So the way that I remember it is that this looks something like an A, kind of an arch shape. So if we were looking at this from the surface, we knew that there was a fold here, we knew it were an anticline, then we would know that these are the older rocks here at the core. So this rock here, as you can see, right, is going to be older by superposition than this and this. Anticline is sort of a shape. Older rocks are in the middle. So if we saw something like this, maybe it was an anticline, we would know right away that the oldest rocks are going to be right here in the core of the anticline. This is its opposite, a syncline. So it's instead of an A, it's sort of bend downward. And here it's in the form of a trough. So we have the youngest rocks here in the core of the fold here in the center. So if we look, we have oldest here at the bottom and the youngest here at the top. And with this sort of fold, it is the youngest rocks that are exposed in the core of the fold. So in this case, if we just look at this part here, what we would expect is to see the youngest rocks here in the core of the fold. And what we're actually looking at here is a syncline, anticline pair. So syncline over here, this sort of trough shape, and it actually shares a little limb here, this part of the fold, with an anticline over on the left. I'm talking about how folds sort of come in pairs and tend to be connected to one another. This is what that means. We also have a monoclonal. So this is not an entire fold. Instead, we just have this one bend, this one sort of change. So we have a flat line, and then we bend, and then we are back to flat line again. Very, very simple. We have a slight bend in mostly parallel layers of rock. Here. Parallel layers, and then right here we have this bend, and then we are back to parallel. It's not a full fold, it's just one bend. So something to be aware of, like in our case here, formation of the Appalachian Mountains. These folds aren't exactly the same as topography. So just because something is a mountain does not mean that it is an anticline. Just because something is a valley does not mean that it is a syncline. As in, for example, here. So we fold these layered rocks up in a series of anticline, syncline pairs like this. But depending on how it is eroded and what happens to rocks long after they are folded, you might have a case like this. Here we have an anticlinal valley. So it is an anticline, like you can see up here, it makes the A shape, but because of how it's been eroded, it formed valley. Likewise, this is a syncline, this part of it here, the little trough shape, but because of how it has been eroded or uplifted, it forms a ridge. It's a topographic high point. And this is looking again at the Appalachian Mountains, a little bit more on the geology of them here. Case where something long in the past has smashed into the outer edges of the North American plate. So these are a little bit more unusual sorts of folds here. Unusual just in the sense that they're a little bit more complicated. You have to think in 3D for these domes. So these are a bit like anticlines, but in 3D. So all of our layers dip in all directions away from the center of the structure, just like you would think of the dome on a building or anything else. This is a case where we have oldest strata in the center, just like anticlines. Strata, we're talking about layers, so our oldest layers are in the center here, and then they dip outward and downward in all directions. It's a three-dimensional A, is maybe one way to think. So this is generally going to be caused by compression and uplift. I'd imagine we have a big magma chamber that is slowly rising up towards the surface, and as it does that, it pushes all the layers above it up into this sort of dome structure. And you can see this spectacularly here. This is in Utah again, this sort of dome. So here, this is going to be the very oldest. Everything else is sort of dipping down away from it. Opposite of this is going to be basins. Youngest are in the center. These are sort of like synclines, sort of troughs, but in 3 dimensions. So all the layers dip toward the center of the structure. They all dip inward. So this is dipping inward towards the center of the structure. These are going to be caused by compression, downwarping. We'll talk a little bit more in the lab about exactly how these might form. So answer 2. What causes these to form? Have more on that one in the lab. The youngest layer is going to be exposed in the center. And it can be a little bit difficult to sort of see what's going on with these because basins tend to get filled in with other things and maybe just look like these big flat areas. But this is one example of a basin here in the Sahara Desert. See, all this here has been filled in. All of our layers are dipping inward, sort of going down inward towards the basin. You can have cases where folds are plunging. So we take our sheet and we fold it up, and then what happens? We tilt it forward or backwards or sideways somehow. And now we would say that it's plunging down into the ground. Right? If I do this, you can see that the part of it that is closest to you is sort of plunging down into the ground. And as a result of this, we have a fold that has been tilted either towards the front or the back. So we have this non-plunging fold over here, and then what happens? We tilt it a little bit, get it a little bit off-center, and now this pattern right here, which looks like the fold, is what it's exposed at the surface, as opposed to a non-plunging fold where you don't see this exact same pattern. Right? You would see the rock layers going in sequence like this. So generally, nature is never going to give you something like this. all anticlines and synclines that you would actually find in nature are going to have some degree of plunge to them, going into the ground in some direction. So if you look at this one right here, notice that it is plunging down in the direction my cursor is moving here. And if you go far enough in that direction, you see that this rock there actually goes into the ground. And we start moving up through the folds of the rock layers. So this is a couple examples here. We have a plunging anticline here, anticline which is then tilted, so it's plunging down into the ground, and the opposite, so a plunging syncline here. And this diagram, which sort of visualizes a case where you might have both. So a plunging anticline next to a plunging syncline, next to a plunging anticline. And notice that these are all plunging in the same direction, but the pattern that you get at the surface is a little bit different for each one. So in this case, our anticline, the plunge is in the same direction as this, the A shape. And for the syncline, the plunge is in the opposite direction of where our V is pointed. Try to hang on to that. So what are some examples of folds? This is one example here in Greece. It's worth mentioning. When we talk about folds, there's always this question of like, how big are these? What sort of scale is involved? Folds are an example of something in geology that is scale invariant. So folds can be literally this size, the size of this sheet of paper here. They could be on the order of millimeters, tiny, tiny little things. Or they can be huge, as in some of these examples, massive folds. These can be any scale. And here, just to reiterate, this fold from Maryland, notice this is a syncline, this sort of trough shape, but it forms a hill. These are two different things. Just because it's a syncline does not mean that it is a valley. Just because it's an anticline doesn't mean that it is a hill. We have differences with this. This is from France. Have this anticline and syncline pair right here. Very, very sharp 90-degree angle here. This is really, really unusual to have something that is bent quite so perfectly 90 degrees like that. Here, Cornwall, UK, this is a massive amount of compression involved in order to get the rock layers to look like this, folded so close to one another. It's also amazing to see that there's this sort of perfect triangular shape to it. It hasn't been rounded off at all. And here in Canada, you can see, so we have this big, beautiful anticline, syncline, fold pair here. And this isn't something that's just present on this one. You can actually see it going back into the others, the same pattern for each of them. Here, there's like a basin in the Sahara Desert. Very unusual example here in Libya, where, to be honest, I can't tell entirely what is going on with this one. It looks like we have a little bit of a syncline that has been upturned or moved off center somehow and exposed to the surface. Really, really unusual stuff there. And here in southern Israel, looks like we have a folded piece here, and then there's been some sort of break, and another part of the fold has been shoved up close to it. We have another part of a different fold over here. Very, very interesting combinations of these. So what are the big ideas? Well, the first thing you would need to know is that the last numbers of the access code are 8, 3. You need to be familiar with the 3 types of stress that we've covered, the 4 factors that might affect rock deformation. What are these 4 factors? What are the 3 types of faults and the associated stresses along with them? And what are our 5 types of folds that we have covered? Thanks.